Hello friends, welcome to C Feel Academy, another video. C Feel Academy, where we learn together from each other. So today's topic is insertion sort, which is probably one of the simplest sorting algorithms we have or we discuss in computer science. So let's get started. So these are the items which we are going to cover today. So we will start with a little bit of basic introduction from insertion sort. Then we will look at the basic idea about the insertion sort. What is the general logic or intuitive idea behind the sorting algorithm. We will then see the algorithm pseudocode or the steps which will demonstrate how to do the insertion sort. Then we will try the insertion sort with an example. So the example is in fact very detailed. We'll go through step by step through the iterations and the steps of the algorithm, and then we will come to the complexity analysis. We will see how the insertion sort performs under various scenarios, that is best case, worst case, and finally before we end there is an exercise for you guys which you can try it out. So cool. So first of all, let's explain what the sorting problem is. So in sorting problem, essentially we are given an array or a list of n items which we can label from a1 to an. Let's say they are in a sequence and we label it from a1 to an. And what is the output? What is our need? What do we want? So we want to reorder those items in a way such that the first item is less than the second item is less than the third item, and so on till we have the second last item, which is an minus 1 is less than an. So this is what sorting is. So which means we want to order the numbers. Let's say if we are given an input of numbers in ascending order from the smallest item to the largest item. So that is the required output of our sorting algorithm. So what is insertion sort, and how does it work? So insertion sort, as I said, is a very simple algorithm, probably one of the simplest which exists, and what it does is it builds a sorted array, which means every time it builds or increments the sorted array by 1, and then it keeps doing that till we complete the entire array. And as I said, it is probably one of the simplest algorithm. It is stable. A stable algorithm means basically items, if there are two items of same value, their order, whatever appeared in the original sequence, still remains in place, which means we don't need additional amount of space to sort an array. And online, so online is a very important property which is probably pretty much popular these days. So online means when we say an online algorithm means as and when new items come, it can work in a streaming use case. So let's say I already have a set of sorted items and my new items are coming one by one. So I can accommodate the sorting algorithm so that the new items are processed and still maintain my property of sorting. So that is a pretty important property which is only present in insertion sort, I would say, in the simplest sorting algorithms. So the best example of insertion sort is sorting cards in a hand. So if you have ever playing cards, and when we pick up cards from the distributed set of cards given to us, we pick up one by one, and then we tend to arrange it. We pick up the next card, we put it in its place in our hand, which is a list of sorted cards. So that's probably the simplest explanation of, or a real-time example of insertion sort. Alright, cool. Let's start again, or let's start with the basic idea behind the insertion sort. What does it do? So the basic idea is we always maintain two partitions of the array, or two parts of the array. The first is the sorted part and the second is the unsorted part. In fact, when we start the algorithm, we will only have one item in our sorted array and rest of it will be unsorted. In fact, so let's say I have this array and initially I'll only have one item in itself is sorted and the rest of the item is unsorted. So this is how I'll start, by dividing my array into two parts, and then what I'll do is from the unsorted array I'll just pick the next item that comes, whichever items comes, and then I will go through my sorted list which is already there and insert it into its appropriate position. So which means I might have to do some comparison with my existing list or existing sorted list, and then I might have to move some items because I need to make space, and then I will insert the new item into its position. So that's how it looks like. So I have a sorted part, I have an unsorted part. From the unsorted part I pick the first item. I'll keep comparing like this from the last item to the first item till I find a space or a point where this new item should be inserted. Once I found that space, I'll then move and make space. I'll move these items one by one and make space and insert the unsorted item to its place. Once I have done that, then I will move my marker so that I'll increase my sorted value to here, which means I increment my sorted array and my unsorted array decreases by 1. Then I just keep repeating the process, which means we pick up the next item and then we insert it into its appropriate process. We keep doing it till we are left with no more items, which means the entire array that we have is now sorted. So that's the basic idea behind it. I hope that helped to understand the basic idea or the intuition behind it. So let's now get into the pseudocode to see how it works. Now if the pseudocode is a little confusing because the steps I and J or things are confusing, don't worry about it. In the next few slides we will also see an example, so that will make it pretty clear. So here is the insertion sort algorithm. So first we are given an array A, which means the array A which has items from A1 to AN. So this is how the array looks like. So we start from, the first step is to start from j equals to 2 to the length of the array. So which means we essentially start from the second element to the last to every element, and then we assign key to aj, which means we pick the first item from the unsorted array and then we insert it to the sorted sequence, which is from ai to j minus 1. So at a particular stage, if we see j is somewhere here, which means this is the item we are picking, this is our key, and then what we do is we start and then insert the item key to the sorted part of the array. So that's what step 4 does. So from step 4 to step 7. So in step 4 we assign I equal to j minus 1, which means we start from the item, the first item from the sorted array, and then till I value is greater than 0, which means till we cover all the sorted items, and till ai is greater than key, which means till we I have that, you know, my sorted item is greater than the key, I keep moving the item, which means ai plus 1 is aij, and I make space for my key. So which means because ai is greater than key has to be before ai inserted, so I have to move ai to ai plus 1. I keep moving it, and finally I make space where the key should be, and I insert my key to its value, insert my key to its appropriate position. So I keep doing it till my I, so this loop continues till I is 0 or I find my position, which means key is less than ai. So if ai is greater than key, I'll just keep moving the items, and once I'm done, then I will assign ai plus 1 is equal to key, which means I'll insert the key to its appropriate position. And once that is done, I increment the j again to the next point, because now my sorted array, sorted part of the array has increased, and then I will keep doing it till I am done with all the elements in the unsorted array. Okay, cool. So let's see this algorithm into action with an example, so that will probably make the things much more clear. We'll go through the steps in very detail actually. So let's see an example. So we are given an array which looks like this, so which means we have 9 2 7 4 3 11 6 5 10, and and we have to sort this array. So so let's go through the algorithm and apply it. So the first step is for j equals to 2 to length a, which means let's first assign j equals to 2. Okay, to start with, we have since to start with, as we discussed, we have to first divide the array into unsorted and sorted part, and when we start, the first element is already sorted, which means 9 by itself is sorted. So hence our sorted and unsorted array looks like this. So the shaded one is the sorted, which is 9, and the rest of the array elements are unsorted. And then we apply our algorithm. So our algorithm says assign j equals to 2, so which means we assign j equals to 2, which means it points to the second element of the array. Then step 2, which is do key equals to aj, so which means the value of the jth location, which is 2, is now stored in key. So we take element 2 and store in the variable key. Now the next job, which is step 3, it says insert aj into it appropriate sequence a1 to j minus 1, so which means from a0 to aj minus 1. So hence we take an variable I, which points to j minus 1, and then we will decrement this value I till we reach the end of the array, and then finally insert the value key into its position. So we now come to step 5, where we have while I equals to 0 and ai is greater than key. So I is already greater than 0 because I value is 1. So let's see if ai, which means 9, is greater than k. In fact it is, 9 is greater than key 2. Hence we have to go inside the loop, which means we go to step 6, which is ai plus 1 is ai. So that means we now move item a1, which is 9, to a2, actually a2, which is 2. So we will basically push item 9 2 and replace 2 with 9. So we just copy the item 9. Once we do that, then we will decrement I equals to I minus 1, which means I now becomes 0. And then we, because it's a loop, we will again go to step 5 to check the condition there. Now in this case what we have is I is already equal to 0, so I greater than 0 will fail now, and hence we will have to break this loop now. So which means we are already done. So in other words, the item 2 has found its place. Why? Because we have compared all the elements in our sorted list, and then we what we do is we now copy the key to ai plus 1, which means we replace a1 with key. So now 2 will replace 9, which gives us this array. So now 2 replaces 9, and we have the array as 2 9 7 4 3 11 6 5 10. In fact, if you look at it, we now completed the innermost loop, which means we now have 2 items as sorted. We started with 1 item as sorted, now we have 2 items as sorted. So our sorted list now contains 2 items, and our unsorted list now contains the rest of the items, which is 7. So in fact, we are done with step 6, but then we are still inside a loop, which is the for loop for j. So we have to go to step 1 again, and in fact we go to step 1 and we increment j. So j now gets increment from 2 to 3. So j now points to 7. Cool. So this is one pass of insertion sort. We sometimes call the inner loop, or when we have placed one unsorted item into our sorted list, we call it as one pass, which means we are done with one item. Now we move with the second item. So let's see what will happen. So the next item, so we'll start with the same array. j now points to 3. Now we go to step 2, which means we assign key to aj. So key now becomes 7, and then we go to step 4. I now becomes j minus 1, which is 3 minus 1 2. Now we come to the inner loop, which is we compare if I is greater than 0. I is definitely greater than 0 because I is 2, and ai is greater than key. So ai is 9 and 9 is greater than 7. So which means we need to push 9 towards the next part of the array and make space for key. So we push 9 towards 7 and we get this array. So now 9 will replace 7. Note, we have still not done anything with the key, but now we decrement I in step 7. I equals to I minus 1. So I now points to the first item, which means I is 1. 2 minus 1 is 1. And notice how in this loop, rather than the previous one, we have to do again a comparison between ai and aj, because I is still greater than 0. And let's see if ai is greater than key. So ai is 2, 2 is less than key. So we don't need to move any more items, which means we break out of while loop and we will replace, which means we will go to step 8 and then replace ai plus 1, which is the second item, and replace it with our key, which is 7. So this is the final array we have. We have 2 7 9 and then the rest of the items. And notice we have covered one more iteration of j, which means now we have 3 items in our sorted list and only 6 more items remaining for unsorted. Cool. So I hope this is making things more clearer, because in the next step probably we will go a little faster, which means we will not demonstrate the comparison of I anymore, because I think it is pretty intuitive. So let's go to the next step. So in the next step, what will happen is j would have incremented by 1 more, which means j increments from 3 to 4, and we reach step 1 again. So let's see the next iteration. So this is the next iteration. So I have j as 4, and then the first step, if you remember from the algorithm, we will store the value of aj, which means 4 now becomes key, and now we will compare key with the we'll first assign I as j minus 1. So I points to the last sorted item, or third, which is now pointing to 3. Now we will compare 9 with 4, and notice 9 is greater than 4, which means we need to push 9 and make space for 4. So we will replace 4 with 9, and this is how it looks like. And next step is to decrement I, which means I will now point to 7, and now we compare AI, which means 7 with 4. In fact, 7 is greater than 4, so we need to push again. So now 7 will replace the next item, which is third, I equals to 3, which means 7 will now replace 9. So we have 277 now, 277, 9, 3, 11, and the next step is to decrement I will now decrement to 1, which is now I is pointing to 2. So 2 will be now compared with 4. In fact, 2 is less than 4, so our loop, inside while loop, will break here, which means we no need to decrement I more, and we can replace AI plus 1 with key. So 7 will be replaced by our key, which is 4, and we are done with next iteration for J. So our final array at the end of this J iteration looks like this. So we now have 4 items sorted, 2, 4, 7, 9, and the rest of the items are unsorted, and J will now move to its next iteration, which is 5. So notice what we have done. So every time we take a J as key, and then we move to backwards in our sorted array, and then we insert the item into its place. So cool. So now we will move a little faster, because we need to go through a few more items in the list, and I think the process probably has become much more intuitive. So this is how it looks like. So J is 5 now, which means key will be picked. So 3 is now assigned to key, and in fact key will now be compared through these items one by one, starting from 9, 7, 4, 2. So when it's compared with 9, 9 will swap 3, because 9 is greater than 3. 9 is greater than 3, and I is 4, so we will swap 9 with 3, so that will give as 9, 9. Next, 7 will be compared with 3, so 7 is still greater, so 7 will now replace 9, so which will give 2, 4, 7, 7 again, and I's value is decremented to 2. Now 4, so value is 4, 4 is still greater than 3, so which means 4 will again get pushed, and we now have 2, 4, 4, 7. So finally I will point to 1, but now the value of I, which is 2, is less than 3, so no need to push any more items, and we just replace key with the second item, which means 3 will replace 4 now. 3 will replace AI plus 1. So that gives us 2, 3, 4, 7, 9, and see, now we have 5 items as sorted, and we only have 4 items remaining to be sorted. So J's value is incremented again to 6. So J's value is incremented to 6, so which points to 11. So we'll start with assigning key as 11, and then we'll keep comparing it with previous items, which means first we'll start and compare with 5, and notice that this iteration will end when this iteration will end, because this should be 9 here. The first we compare 9 with 11, and 9 is less than 11. Since 9 is less than 11, we no need to push 9, and in fact our iteration or the inside while loop will break here, so which means we don't need to do any swaps here, since the inside for loop went. So inside for loop is broken, inside while loop is broken, sorry. So now we will have our 6 items as sorted. Notice, because if you intuitively, if you notice, 11 is already in its sorted place compared to the entire sorted items, which is 2, 3, 4, 7, 9. So now we will pick next item, which is J. J now becomes 7, and key now becomes 6, and 6 will be compared with the sorted items, which means 6 will be compared with 11, and 11 is greater than 6, so 11 will replace 6 first, then 9 will replace the position of 11 and 7 will replace 9. So here I have skipped the I iterations or I loop, and notice finally what will happen is key 6 will go and replace the position of 7, will get inserted at the position of 7. So my next J loop will have 7 items, and 7 gets inserted, 6 gets inserted into its position, and all 7, 9, 11 are actually moved one item, or one moved one item to the right. So next is J equals 8. So 5 will be picked and stored as key, and 5 will be inserted at its position. So notice where it will be placed, because 5 has to be placed somewhere here because it lies between 4 and 6. So we will have to push all these items one step or one space to the right, and then insert 5 in the place of 6. So at the end of J iteration, we'll have 5 also inserted in its place, and one more item in the sorted list. So which means we'll have 2, 3, 4, 5, 6, 7, 9, 11. Now J has incremented to its final value, which is J equals to 9, and 10 is assigned or copied as key, and 10 will be inserted into its place. So 10 is somewhere here, 9 and 11, so which means we will push all these items to the right. So 11 will get pushed and replace 10, and key will be inserted at place of 11. So finally we have 10 also in its place, and since J has reached to its final value, which is n, in our case n is 9, so we are done with all the items now. We don't have any other unsorted item, and finally we are done with our final sorted array. So cool. So last few steps were a little fast, but I'm pretty sure you guys understood it, what we are doing. So just placing the key into its value. So finally we have reached the place where we have sorted the array using insertion sort. So I hope this process was clear. If not, feel free to comment, and I will create another video explaining any of the steps that appeared confusing. So before we come to the exercise, let's do a little bit of analysis of the algorithm. We'll do a complexity analysis or performance analysis to see how insertion sort performs. So basically, insertion sort, if you notice, the algorithm has two loops. There is an outer for loop which runs from j equals to 2 to length of a, which means j equals to 2 to n. So roughly it runs n minus 1 times, so which is close to n, so let's assume it as n times. And then the inner loop, while loop, which starts from j minus 1 to 0. So let's say about j times the loop runs, or j minus 1 times j times the loop runs, and then we do some stuff inside each of the loops. So this is how the algorithm looks like. So we have one loop inside of the other. So let's see what happens in average case. So average case of an algorithm means assume that we have items in mixed, which means it's neither fully sorted neither fully unsorted, some sort of mixed items we have. So assuming let's calculate the total number of comparisons. So if you remember, in the first case, the inner loop will only run one time because j value is 2 and I will be from I will start from 1 to 0. So there is only one comparison done. In the next case, as j increments, the number of comparisons also increments, which means it is 2, roughly assuming the inner loop is not broken. In fact, yeah, the inner loop is not broken, and we have roughly about 2 comparisons. So similarly, the number of comparisons increases to n minus 1 in the last iteration. So if we add all of them, we will have it as n into n minus 1 by 2, which is n square, or roughly it's n square, order of n square. Same thing is with worst case as well. In fact, worst case and average case has no difference in case of insertion sort. So let's say the array is reversely sorted and we need to still make those many number of comparisons. In fact, in case of average case, the inside J loop might break early, so we may have a little less number of comparisons. But in the worst case, it will exactly have order n square comparisons. So assume the array is reversely sorted. So what happens in best case? So in best case, let's say the array is sorted. We already have a sorted array, which means something like 1 2 3 4 5. So in this case, what happens is J keeps incrementing, but notice we don't need to do any swaps. Why? Because the items are already in their place. So when 2 will be compared with 1, the inner J loop will break. So inner J loop will only have one comparison, and then J will increment and 3 will be compared with 2. So in approximately the inner loop only runs one times, because there is only one comparison done in the inner loop. So which means we only have the outer loop, which is n times, and inner loop is always 1. There is always one comparison. So we will always have 1 plus 1 plus 1 n times. N times we will have 1, so which is actually just n, which means it's actually order n. So notice in best case, we are just done with order n. Now if complexity analysis is a bit confusing, I will make sure to post another video where we discuss with with complexity of algorithms, so that might give a simple intuitive idea of algorithms and how do we and why do we compare the algorithms. I'll make sure to link the video here for convenience, and then you can come back after visiting that video so that this analysis will make much more sense. Alright, cool. So we notice that insertion sort takes order n square for average case and worst case, but in case of best case it's order n, which means it's linear. So I think that's all I have for the insertion sort. In fact, before we end, here is an exercise for you. So here is a given an array. Again, it has 9 items and it has certain items which are unsorted, and the exercise is to sort the array using insertion sort, and also list the total number of comparisons needed. So which we didn't do in our example, but I would request you or recommend you to keep a track of the comparisons that you did, so that it will give a fair idea or give a much more clear understanding of the insertion sort. So cool, finally we are at the end of the video. I hope you liked the video. If you have any comments or suggestions, or if anything was confusing, please comment at the in the video, and I'll make sure to attend to it. So please also go through the other videos on our channel, and if you have any specific request for any algorithm to be covered or any item in computer science to be covered, you can do so. So thank you, and see you in next video. Bye bye.